Hi friends, good morning. In the last session, we have seen what is meant by resistance and what all the parameters will affect the value of resistance. From this, we conclude that resistance is directly proportional to the length of the conductor and inversely proportional to the area of the conductor. Also, it is depends on the resistivity as well. So for the materials and all, the resistivity is very less, but the insulators are having more resistivity, right? So that accordingly the resistance of the insulator is also high. So then we have seen another one. The resistance is also vary with respect to temperature. So today we are going to learn about what is meant by Ohm's law and what are the conditions we have to be considered in the Ohm's law. First, let's see that already we know the resistance is the function of the temperature. That means some cases when the temperature increases, resistance will increase. In other case, when the temperature increases, resistance will decrease. If suppose normally in these materials and copper, aluminum conductors and all, when the temperature increases, resistance will increase. Similarly, when temperature reduces, resistance will reduce. That's why that type of materials will come under positive temperature coefficient. Then next one, negative temperature coefficient. Normally semiconductors such as silicon, germanium and all, when the temperature increases, resistance will decrease and vice versa. So we cannot directly implement this increase in temperature and decrease in temperature, how the resistance values will be very directly in the equation. So that is a separate research. So today we are going to learn about Ohm's law. In this Ohm's law, normally the temperature of the conductor should be remains constant. When the temperature of the conductor remains constant, only the resistance will vary with respect to the length of conductor or area of the conductor and resistivity, right? So let us see the Ohm's law. The Ohm's law states that when the temperature remains constant, voltage across the conductor is directly proportional to the current which is flowing through the conductor, so that the constant of proportionality is called as resistance. That's why we used to say V is directly proportional to I, and then V is equal to R into I. R is called as the constant of proportionality and we will call it as resistance. So from this we can conclude that voltage is linearly varying with respect to current when the temperature of the resistance or conductor is constant. When the temperature of the conductor remains constant, voltage is directly proportional to current. So that is a linear relationship. Then let's see now one circuit. We are giving this voltage and the resistance is connected in the circuit. There is no other element in the circuit. Therefore, normally the power applied to the resistor is, we will call it as V into I. We have two types of power, AC power and DC power. For time being, you consider the DC power. The power formula, I will let you know the next module what is meant by AC power. So the power applied to the resistance is nothing but voltage into current. Let us see now. But in your Ohm's law, already we know V is equal to I into R. From this we can understand what is equal to I. I is nothing but V by R. Therefore, the power dissipated in the resistance. So that resistance is the only element which is connected in the circuit. So whatever the power V into I given to the circuit, it will be dissipated by the resistance. So the power dissipated by the resistance, we already know V is equal to I into R. In the power equation, V is equal to I. If P is equal to V into I, if we substitute the voltage, so we will get I squared R. We can say I is nothing but V by R. If we substitute again, V square by R. There is no other elements in the circuit. Therefore, we can say that power dissipated by the resistance is nothing but input power V into I. or otherwise I squared R or V squared by R. That means current I is nothing but current flowing through the resistance and V is nothing but voltage across the resistance. So in this circuit, as the resistance is connected, only the element connected in the circuit, the voltage across the resistance is nothing but the voltage applied to the circuit. So now assume now when the number of resistance are connected in series or parallel. So if how you will find out the resistance, power dissipation by the resistance. So already we know the equivalent resistance. When the resistance are connected in series, R equivalent we will write R1 plus R2, or otherwise R equivalent is nothing but R1 R2 divided by R1 plus R2. This is for when the resistance is connected in two resistance are connected in series or parallel. So if you want to know what is the total power dissipation in the resistance when the resistance are connected in series or parallel, what we have to do? First we have to find out equivalent resistance of the in the particular resistance. That means two resistance are connected series means R equivalent equal to R1 plus R2. If the two resistance are connected in parallel means R equivalent equal to R1 R2 divided by R1 plus R2. So already we know R equivalent, so that we can find the total power dissipated by the resistance is nothing but power is equal to I squared R equivalent, or otherwise V squared by R equivalent. So this variable, these equations already we have derived from the Ohm's law. So I hope you understand how the Ohm's law can be applied to measure the power dissipated by the resistance in the circuit. So let us see now next the inductance. So let us recall the right hand thumb rule for identifying the current and magnetic field in the direction. Normally the inductance will come to the picture when the magnetic field effect is there. Then only the inductance term will become. So normally if you see this, assume that right hand, the thumb finger, and that assume this four finger remaining except the thumb finger, you make this position like the shown in the figure. Assume this red arrow direction is the current flow direction of the current. When the current is flowing in this direction, direction of that perpendicular direction of the thumb finger, the magnetic flux will be produced like this in this direction. The remaining four fingers, how the direction will be, that direction magnetic flux will produce. For example, this is the conductor. Now the current is, this is the conductor and the current is flowing through. The direction of current is like this. So now if you see this, the magnetic flux direction is in this direction, anti-clockwise direction. At the same time, if the current flowing through the conductor is opposite direction, magnetic flux will be clockwise direction. So the current direction, with respect to current direction, the magnetic flux direction will change. When it is going up, magnetic flux direction will be anti-clockwise direction. When it will going down, magnetic flux direction will be clockwise direction. So you should know this, how the magnetic flux is created, so that it will be very easy to understand how one can derive the inductance equation in the next slide. Assume now there is a solenoid. There in this solenoid, the length of the solenoid is L, and the voltage which we have applied to the winding is nothing but V. Therefore, the current will flows to the circuit, right? That in solenoid, the current will flows to the solenoid. So when the current is flowing, as per our the same thumb rule, the current is flowing this direction. Assume that finger, all four fingers. We can consider this in the different way also. Current is flowing in this, the finger, all remaining four finger direction. Therefore, magnetic current, the magnetic flux will be in the direction of the thumb finger like this. So now if the current flowing to the direction is just opposite, again now in this case current flowing flux created by this magnetic solenoid is clockwise direction. At the same time, if the current is direction is changed, the magnetic flux direction will be opposite direction. That means anti-clockwise direction. From this, we can find out the magnetic field intensity is nothing but number of turns in the current flowing to the conductor divided by the length of the solenoid. So the number of turns already we know that we have now 5 turns are there. So number of turns n, then I is nothing but current which is flowing through the solenoid, and L is nothing but length of the solenoid. Now from the BH curve, we have already studied the magnetic flux density is nothing but mu into H. Already we know this magnetic curve and BH curve everything. From this we can derive this B is equal to mu into H. So then mu is nothing but magnetic permeability is equal to mu naught into mu r. Therefore mu naught is nothing but permeability of the free space, that is 4 pi into 10 to the power minus 7 Henry per meter. Mu r is nothing but the relative permeability. It is 1 for vacuum and greater than 1 for the materials. Based on the materials, based on the material which we have used in the magnetic circuit, the mu r value will be varied. Assume I got this from this research gate, the content, see the substances in the left side. Air is having relative permeability of 1. At the same time, aluminium also more or less 1. Then Xerox cube having the relative permeability of 1500, and mild steel is having the relative permeability of 2000. So this is the just for understanding how the relative permeability is varying with respect to the material. So now from this, when the permeability is increases, magnetic flux will pass easily. Already we know flux is magnetic flux. When the permeability of the material increases, automatically magnetic flux density will increase. So the magnetic flux will easily pass in the magnetic circuit. So from this, from the equation 1, we know that already B is equal to mu into H. Already this equation 1 has given the value of H. So just we can substitute here mu is equal to N into I divided by L. Then magnetic flux density is nothing but magnetic flux per area. What is meant by density? People density means what? The per person, the per particular person in the hall divided by the total area of the hall. Similarly, magnetic flux density is nothing but magnetic flux per the particular area, the area of the conductor. So from this we can see that B flux is nothing but B into area. So we will conclude from this inductance is nothing but number of turns into flux divided by current which is flowing through this. The third equation will give the flux, therefore NBA divided by L. Then we can see this NA divided by L, and already we know the second equation what is equal to B. B is nothing but mu into N into I divided by L. From this we can conclude this final equation. I inductance L is nothing but mu into N square A by L. So from this we can conclude that inductance is vary with respect to number of turns, area of the conductor, and the length of the conductor. So with this we will understand what is the importance of inductance, how one can derive the inductance value. There is having induction two types, mutual inductance and the self-inductance. All those things I will, wherever required, I will explain to that. Now you can study what is meant by inductance. Inductance is nothing but L is equal to mu into N square A by L. Then let's see about that another one, the unit of inductance is Henry. Then let's see the equivalent inductance. So normally the symbolic representation of the inductance is like this. So when this inductance, for our simplicity, I have taken as a box. L1 is nothing but two inductance, L1, L2 are connected across the voltage V. Then what is mean by L equivalent? As like R equivalent, L equivalent is nothing but L1 plus L2. Similarly, the resistance R equivalent also, when the two resistance are connected in series, R1 plus R2. Then when the number of resistance inductance connected in series, so we can see L equivalent equal to L1 plus L2 plus etc. up to Ln. Assume now the two inductance are connected in parallel, therefore we can write the L equivalent is L1 L2 divided by L1 plus L2. The same way as like the resistance what we have learned, if suppose three inductance are connected in series, so we parallel, we can write L equivalent is nothing but L1 L2 L3 divided by L1 L2 plus L2 L3 plus L3 L1. Then if the more number of n number of inductance connected in series, if that case L 1 by L equivalent equal to 1 by L1 plus 1 by L2 plus 1 by L3 etc. up to 1 by Ln. So with this we can conclude the inductance. What we have learned, what all the parameters will affect the inductance, and what is Ohm's law, and what when the temperature remains constant, voltage across the voltage across the resistance is directly proportional to current flowing through the resistance. Then we understood what is meant by positive temperature coefficient, negative temperature coefficient. Also we have seen what is meant by what is equivalent inductance when the inductance connected in series and parallel. The next lesson we will understand what is meant by electromagnetic induction and Lenz's law with some animation. Also we will learn about the capacitance. I hope this topic is very much understanding and interesting. Those who have not subscribed this channel, kindly subscribe and share and like as well. If you have any feedback, kindly comment on it so that I can correct in the future videos. Wish you all the best. Thank you.